In this video of our college algebra final exam review, we're going to start by talking about the invertible functions. Remember that a function is a function if it passes the vertical line test, or another way to say that is a graph represents a function if the graph passes the vertical line test. And in both of these cases, they do. So we do have functions here, but only one of these functions is invertible, or in other words, has an inverse. And the way we determine if a function has an inverse is we apply the horizontal line test after we've applied the vertical line test. Both of these passed the vertical line test, but only one, this guy over here on the left, passes the horizontal line test. Because no matter where I draw these horizontal lines, they will only strike or touch the graph in one position. That means that this function is 1-to-1. Over here on the right-hand side, there are a whole bunch of horizontal lines that can be drawn that would touch or strike the graph in more than one position. Therefore, this function is not 1-to-1. Therefore, it does not have an inverse, at least on this domain. If we had limited this graph, let's pretend like this portion of the graph didn't exist, or that we weren't interested in this portion of the graph, and only focused on this one instead, well, this portion of the graph is invertible, and so by restricting the domain, we can find a section of it that does pass the horizontal line test and therefore would have an inverse. So we could find an inverse function for this component of the graph, but that's not really what this particular question is asking. We would say that f of x is invertible because it is a function and it passes the horizontal line test. Now, since the inverse of a function essentially is the opposite of the original function, where the inputs and the outputs are reversed, we could sketch a graph of the inverse of this function. Even though we don't know what the equation of the original function is, we could still find its inverse. There are two ways to do that. We could imagine a diagonal line right through the origin and reflect every point that's on the original graph across this imaginary line. The other thing that we could do, and perhaps might be easier since the graph has been presented to us, is to identify components on the graph, nice whole number coordinates, for example, and reverse the x and the y coordinates. For example, this coordinate here is 4, 2 in the original graph, so the inverse graph would have the coordinate 2, 4. This coordinate here is 3, 0, so the inverse function should have the coordinate 0, 3. And we could do this for every coordinate on the graph, but I think doing so for just a handful of them would be appropriate. This one at 0, -1 becomes -1, 0. This one at -3, -2 becomes -2, -3. And this one, this is kind of interesting, -4, -4 becomes the same coordinate, -4, -4. Now, if I connect these new data points with a sketch, we've got ourselves a picture of the inverse function, which coincidentally, this inverse function will pass the vertical and horizontal line test. Also, it is a mirror copy across the equation y = x, or this diagonal line down the center. Now, one could argue that the same approach could be used over here on the right-hand side, so I've taken a few points and just reflected them across this line. When we draw this resulting image, however, you should very quickly notice that this graph does immediately fail the vertical line test. And so the inverse, air quote, inverse here, is no longer a function itself. And since the inverse is not a function, it makes this resulting equation a little bit more difficult for us to use in the context of this class. So that's why we haven't really been considering them. I don't have any examples of even, odd, and neither functions in this particular review, but there are plenty in Math Excel for you to investigate. Do recall that even functions are those that are defined this way, that when we substitute an opposite of x into the original equation, we ended up getting the same y value as our original function f of x. That's the definition we used for even functions. We said that odd functions were those that were defined in much the same way. When a function is evaluated at the opposite of x, we ended up getting the opposite of the y value of the original function, and there's certain symmetry associated with each of those. So if you go back and review those definitions, you should be just fine with the questions regarding even, odd, and neither functions. With regards to the exponential equations, the test was written, or the questions that I used for this test was written in this format, a times b to the x power. However, in class, we almost exclusively used this format, f of x equals c times a to the x. So I'm going to ask these questions in that format here. The a value and the c values are what we're asking about. Now, the c value we defined as our initial value, our starting point of the graph, or our starting point of the function, and we called a our growth rate or growth factor. And if we're being asked about this this question here, to arrange the four values in decreasing order, the four c values in decreasing order, we're talking about the four initial values to these functions over here on the left-hand side. Now, generally speaking, with an exponential equation, we talked about it looking like this. This is an exponential growth function, where c, our initial value, is the value of the function right at the y-axis, or when x is equal to 0. Whereas a, our growth factor, indicates the percentage growth from one step to the next. So a is really a measure of percentage growth, and a is always a value that's greater than 0. It's always positive. When it is bigger than 1, we have a growth rate of an exponential growth expression, where the graph continues to increase from left to right. When a is less than 1, we have a decay rate, or a graph that decreases from left to right. But in all cases, the a values are positive. Now, to answer this first question, looking at the c values, well, that's us describing the values here right on the y-axis. And the graph that has the largest c value is here, y3, the equation y3. The graph that's got the smallest c value is down here, y4. And if we're listing in decreasing order, we would start with y3 and end with y4. In between, the next largest from after y3 is the graph y2, and then y1. So that's the order of equations with c values in decreasing order. As far as our a values go in decreasing order, again, we start with the largest a value, a being our growth factor. Now, y1 appears to have the steepest line, especially over here at the initial position, but that's not the largest a value. That's not the largest growth factor. In fact, that's the smallest growth factor because this is the most rapid decay. So I'm going to say that y1 has got the smallest a value. The largest a value belongs to this graph here, y4, and that's because it is the steepest growth rate, while the equation itself is actually increasing in size, while it's growing from left to right. The next steepest growth rate, while still positive, belongs to the equation y3, and then of course y2 would be next. It becomes a decay example here in y2, but it's not nearly as steep as the decay example in y1. So on this exam, some of the questions that you'll encounter are less mathematical in nature and more interpretive, and I think those are wonderful questions to ask because it really does get at the heart of the behavior of the equations and the analysis of the equations, rather than just the rote practice of evaluating equations using arithmetic. In fact, in class, we even asked some similar questions about quadratic functions, and that's really what this next bulleted point is really trying to address down here. What do a, b, c, and d do, the discriminants? What do they do to the shape of the quadratic graph? So here are some examples. If I say that the letter d represents the discriminant, I can ask this question. Whereas a, b, and c, those are the values inside the quadratic function itself. And so we should recognize that the a value being positive, when the a value is positive, that's going to create a graph that opens up. So which of these graphs has a positive a value? Well, for this question, we would answer the red and orange graph have positive a values. Which ones have positive c values? Well, again, recalling a little bit about the behavior of our functions, the c value here represents our y-intercept. If x were 0, these two terms would disappear, and we'd be left with the c value, a y-intercept. So where is c greater than 0? Well, that only occurs here at this position. So on our orange graph, we have a positive c value. Clearly, we have a negative c value on the green graph, and our c value on the red graph appears to be 0, neither positive nor negative. Now, with regards to the discriminant you should recall is the component of the quadratic formula that fits underneath our square root symbol. So if the quadratic formula is the method we use to solve for x, which requires the opposite of b to be added and subtracted with the square root of b squared minus 4ac divided by 2a, this little equation here is our discriminant. The discriminant d is b squared minus 4ac. In fact, when I teach my Algebra 2 students, I teach them to use the quadratic formula that looks like this, where x is equal to the opposite of plus or minus the square root of d divided by 2a, and then we memorize the secondary equation, d equals b squared minus 4ac. And this is done to emphasize the fact that when the discriminant is negative, when the discriminant is less than 0, we end up having to take the square root of a negative number, which would lead to imaginary number or complex number results. When the discriminant is negative, that also implies, because of the imaginary number solutions, that the graph itself does not touch the x-axis. As long as the graph touches or crosses the x-axis, then it's either going to be positive or equal to 0. Because again, when we take the square root of a positive number, we always get two results, one positive and one negative. The square root of 81, for example, is both positive 9 and negative 9. If the graph of a quadratic just bumps into the x-axis, we say that there's one solution, and that happens exactly when the discriminant is equal to 0. Because the square root of 0 is only 0, we don't get two results, and therefore we would only see 1 point, not 2 points of intersection along the x-axis. So the last question is a little bit about our b value. What would happen if b were equal to 0? And for that, I ask students to consider what sort of equation, or what the quadratic equation would look like if there was no b value. And so some said, well, this equation has no b value, and this one has no b value, and so on. And so what do all of these sketches look like? Well, that would occur when the quadratic equation has been either flipped or, in its original position, shifted up or shifted down. So here is a sketch of what x squared plus 9 might look like, and here's a sketch of what negative x squared minus 4 looks like. But in any event, if b is equal to 0, the graph itself is aligned on the y-axis. And so do we have any graphs here that would imply that the b value to the equation is equal to 0? And we would say none in this case. So here again, some questions about the behavior of functions are fair game for the final exam, even if there's no true application or numerical analysis involved. If you're struggling with these questions, though, it doesn't hurt to do what I've done here and just make up some examples that meet these criteria and investigate what happens for each of them. So if you're working on a problem and are stuck, by all means, create some test points and see what happens to that equation or graph. Now, speaking of quadratic equations that would need a result, this time we're going to do so without the use of a graph. And we've got 2x squared minus 3x minus 2. So if we recognize that a is equal to 2, b is equal to, let's double check that again, negative 3, and c is equal to negative 2, it might be worthwhile to compute the discriminant right off the bat. so that we can kind of investigate what's going to happen to our solutions here. The discriminant is going to have to be negative 3 squared minus 4 times 2 times negative 2. This turns into 9 minus 4 times 2 times 2, but this negative sign and this negative sign is going to turn positive. So it looks like my discriminant's positive. That means I'm going to have two real number answers. Let's go ahead and figure out what the discriminant is, and that's going to help us with the next step. Well, 4 times 2 times 2 is 8 times 2 is 16, so we've got 16 plus 9 is 25. Oh, that's kind of nice. Because now, when we're looking for our solutions for x, if we think of this alternate form, the opposite of b plus or minus the square root of the discriminant, d, divided by 2a, well, that's the opposite of negative 3 plus or minus the square root of 25, divided by 2 times 2, which is 3 plus or minus 5, divided by 4. And here's where our two solutions come into play. 3 plus 5 and 3 minus 5 are going to produce two different results. One of them is 8 over 4, and the other one is going to be negative 2 over 4. And without factoring, we've been able to now identify the solution, or the two solutions to this particular quadratic, how they exist at both 2 and negative 1/2. Now, whether you use this modified form of the quadratic formula or one that you had memorized from Algebra 2 or prior classes, either one's perfectly fine. But again, since the instructions here said to find the solution using the quadratic formula, make sure that you leave evidence or show your work on how you obtain that rather than just relying on factors or graphs. Now, to finish out this particular video, we're going to address the graphs of polynomials. We just had a test over this, so if this was a traditional question, I probably wouldn't even review it in the video. But you'll notice that this question, again, is giving us some variables, a, b, c, d, e. And so we've got to be able to interpret the behavior of this function without relying on those numbers. Unfortunately, those numbers generally don't really affect the behavior of a polynomial on the large scale. And we can probably answer a lot of these without worrying about those values specifically. So part A, what is the y-intercept of this function? Well, again, we should recognize at this point the y-intercept occurs at the location identified by this constant. So I wouldn't say that the intercept is 1. Don't say that. But the intercept is 0, 1. When x is 0, the y value is 1. And we could see that by essentially substituting 0 in place of x. All of these terms would disappear, regardless of what the coefficients are. What's the degree of the polynomial? Well, the degree is 6. We know that's the largest exponent, and it's generally listed at the very beginning of the polynomial, as long as we're written in standard form. What power function does this polynomial behave like for large values of x? Well, that's kind of a strange question to ask. I think what they're implying here is what does this, or what's the parent function of this polynomial? And so what I would answer off with is y equals negative x squared. Now I say negative x squared because this is the most basic polynomial function that describes the end behavior. And when we talk about large values of x, we're talking about the left and the right hand side of the graph. So extreme values from negative infinity to positive infinity for very large and very small values of x. So in general, since a negative x squared parent function would have tails that point down, and this function, regardless of what we see over here on the right, would also have tails that point down, both of them, I would say that this polynomial originally behaves like this one, our parent graph. Let me put boxes around my answers as we go here. Now, as far as describing the behavior of this function, this is just our way of asking about the tails of the graph again. As x approaches infinity, as we move further and further to the right on this graph, what happens to our y values, the function results? Well, y tends towards, or y approaches negative infinity, because as we move to the right, our y values move down. And so this question is asking what's happening to the function results, or the y values. Those y values are getting smaller towards negative infinity as we move to the right. As we move to the left, as x tends towards negative infinity, well, the y values also decrease. So we would say here that the y values approach negative infinity as well. If you're on the test next week, the final exam, and you kind of forget what's being asked here, but you do recognize that we're talking about the tails of the graph, you could express that in a phrase, and I'd be okay with that too. You could say something like this: the right tail is pointing up, and the left tail is pointing down. Yeah, well, in this case, they're both pointing down, but I'm just saying on a sample next week, if you have to say that, that would be okay. I'll just go ahead and write this as down. So if you say right tail down, left tail down, I think that would be okay for me as far as the behavior of this function. For part F, at most, how many x-intercepts does this function have? Well, we know that the intercepts are real number solutions, so in this particular case, this graph could have as many as 6. It's the number of turning points that is 1 less than the degree, and we would say that there is as many as 5 turning points. I won't ask you to tell me the possible answers for those turning points. That's an analysis that we did not perform in this class, so that will not be part of this test. But it is important to recognize that the degree that we identified prior represents the maximum number of x-intercepts, or real number solutions, and 1 less than the degree indicates how many turning points there could be in this graph. So in a graph that is negative 2x to the 6th power, we know that the outside tails are pointing down. That much we know is true. And it could have as much movement or turning behaviors as something like this, but it could not have any more turns than that because of the degree itself. So I hope this video helps clarify a few things about the exponential, quadratic, and then further polynomial functions. In the next video, we'll pick up with our rational functions and talk a little bit about them. Although that discussion will be relatively short because we did just complete a test over that content recently. In any event, thanks for watching.